Okay, so we're going to start the session. So it's my pleasure to have here Stéphane. Mallat. I'm sure all of you have heard about him. Those of you who are here following the MBA, then you as a professor. Those of you who haven't, I hope you will enjoy it because it's very, I really recommend it. So just to give a little background, Stéphane did his PhD some years ago in Penn State, I believe. In an area that then changed a little bit his research, but he's mostly made really critical contributions to the harmonic analysis. He was one of the fathers of quantum theory that has been. Okay, yes. Okay, so I was saying that Stéphane did his PhD with Regina Bassi, who is now in Berkeley. And then he became very well known because he was one of the fathers of wavelet theory that really changed the way we think about images and complicated high-dimensional signals. And recently he got interested in other problems that are also related somehow to the mysteries of the data start with harmonic analysis. And I think he's going to tell us about some of his mysteries that concern classification and high-dimensional learning. So please, Stéphane. Thank you very much.
It works? Yes? Yes. Okay. Thanks very much. Thanks for the invitation. So yes, I'll be speaking about deep neural network. I suppose most of you have heard a lot about it. But from the mathematical point of view, and what I'll try to do is not at all to explain the full mystery because I think we are all very far from it, but begin by explaining why the problem is so difficult, why it will probably take time to understand it, and still, what is the underlying mathematics behind? And as you will see, it touches many branches of mathematics. And the problem is, in fact, really independently from the network aspect. So let me begin from learning and high-dimensional learning, which is a problem you know well. So high-dimensional because the data that I will write X is a high-dimensional vector in RD, where D is typically potentially several millions. So think of an image processing point problem such as classification. X will be an image, and each point of an image is one coordinate of X. So you typically have, let's say, about 1 million points. And what you would like to do in a classification problem is to estimate a function f of x, which gives you the label of here the image. So, for example, beaver, lotuses, anchors, and so on. And to do so in the learning framework, you have examples. So you have example of images xi, for which you do know the label f of xi. Now, immediately you see the big difficulty of the problem is that there is a huge variability within each of the classes. So what you need is to characterize the class and at the same time discriminate them from the others, so you may think about extracting elements which are invariant to the class and which are still rich enough to discriminate them. Now the same problems appears in regression, so regression problems are essentially the same. The only difference is that f of x here will have a value in R. And I will take example from physics because it will point you the real difficulty of the problem. So in physics, for example, f of x is going to be the energy of the system, and x will describe the state of the system. So for example, in astronomy, cosmology, x will be the mass distribution of, let's say, a galaxy, and what you would like to compute is the energy. Why the energy? Because if you know the energy, then you can compute derivatives, and you have access to the forces, all the interactions. In other words, if you can learn the energy functional, then basically you can learn physics from data without any physicists. Now, if you go to the other extreme, infinitely small, then you get quantum physics. So then, for example, X will be the distribution of the atoms within a molecule. And you would like to compute the quantum energy of the molecule. If you can indeed do so from data, that means that you can basically discover the quantum laws directly from data. Can we do that? So, what is the big difficulty of all these problems? The big difficulty is the curse of dimensionality, which again you know, but I'd like to go back to it. So, if you look at the problem in a naive point of view, it doesn't look so difficult. It doesn't look so difficult because you have example, the different xi. You know the value of the function at xi, which gives you here the color. Now you have a new point x and you want to compute f of x. So the immediate idea is just to do an interpolation, meaning you're going to take the close neighbors and do some kind of averaging from the close neighbor to estimate the value of the function at the point x. Now, why this will never work in high dimension? To do that, you need two things. You need that your function should be regular, and you need to have close examples. And the problem is you never have close examples in high dimension. In other words, the distance between your x and one of the examples will typically be always very large. So if you look at examples, it's quite obvious. You take an image, it's very unlikely that you'll have another image in your database which is close in the sense that if you do the difference, the error is almost zero. You can see that the distances between these images are indeed very large. But that's a direct consequence of dimensionality. Why? Because suppose you are in a cube, 0, 1 to the power d. Suppose that you want to cover the cube with a uniform sampling, like that, at a distance epsilon. How many points do you need? If you are in dimension 2, you will need epsilon to the power minus 2. If you are in dimension d, you will need epsilon to the power minus d points. Now, suppose you take epsilon equal 1 over 10, which is not very small. You take d equal 100, it gives you 10 to the power 100. This is already more than the number of atoms in the universe. So there is just no chance you'll have enough example to cover densely your space. Not only that, but d in our case is not going to be 100, but rather 1 million. So the space is absolutely huge. And the number of examples you have is very small compared to what you would need to be able to do a simple linear interpolation. Now, on the other hand, we can still face this curve of dimensionality. So why is that so? One of the important reasons is the fact that the data, the variables that you have, are indexed by a low-dimensional variable. So what is this low-dimensional variable? If you have an image, all the pixels of the image are indexed by their position, which is a two-dimensional variable. In physics, you have four-dimensional variable, three-dimensional space, and one-dimensional, for example, time. If you take a book in a text, you have the sequence. Now, what's the consequence of that? The interactions are going to depend upon this low-dimensional variable. And typically, when you have, let's take again the examples of physics, or think of pixels, or think of social network. You can look at all the elements of your network. Everybody interacts with everybody, potentially, even at very large distances. But the strongest interactions are very often going to be from the closest variables. And then when you have more faraway variables, they do interact, but you can summarize very often these interactions as an interaction with a group as opposed to with each of them. The consequence of that, which you see all over in physics, which it really has been up to now the science of high-dimensional problems, is the multi-scale factorization of the problem. Instead of looking at the interaction of each variable, you are going to look at interactions at different scales. And if you do that at all scales, you can reduce a problem where everybody interacts with everybody, d-square interactions, to log d square interactions, because you are going to look at interactions of groups as opposed to interactions of each of the variables. That's a very important element, which allows to often go around this curse of dimensionality. So these multi-scale properties, we can expect to see them appearing. It's not at all new observation. These kind of things are known, has been known for a long, long time. And Johan mentions about wavelets. What wavelets are, they are essentially mathematical tools to understand interactions across scales. How do you build up these interactions? How do you understand these interactions? And that's why we'll see these wavelets appear at one point of the problem. Okay, so the overview of the problem, the talks will be the following. I'm first going to begin with a one hidden layer network, just to review the properties. And I'm going to look at it from the point of view of approximation theory, to again raise this difficulty of the curse of dimensionality. So, this will be reviews, and you will see the difficulty of tackling problems in high dimension with classical functional analysis tools. Then I will briefly relate all this to kernel learning, which you've seen in the previous courses, to again see the different strategy to attack these high dimensional problems. And then we'll look at strategies for reducing dimensionality. How can you reduce dimensionality with change of variables? And that's where deep neural networks are going to come in. Now, one of the very important elements that are going to come in are symmetries and groups. Symmetries are all over physics. Essentially, all physics has been rebuilt around the notion of symmetries. For example, if you look at the standard models which build up the interaction between particles, they are entirely based on the fact that there are symmetries of the system. We'll see again the same concept appearing in the framework of data analysis. And then wavelets, why? Again, because of these multi-scale. So, because I want to try to do some mathematics, when you do mathematics on a problem which is so difficult, you begin by simplifying it. And so the question is, how can you simplify a deep network without losing all its power and capturing some of its important properties? That's what we'll begin with these wavelet scattering transforms. And then we'll see what we are losing relatively to these more powerful, totally adaptive networks, and look at applications. There are many open questions behind all that. Most questions, in fact, are open. And just to point out, there is a kind of review paper that I wrote recently, which is on arXiv, which summarizes and gives many references around all this. So we'll cover a lot of what is in this paper. Okay, so let me begin at this problem of learning from the approximation point of view. So our problem is we have a function of very high dimensional variable x that we want to approximate, and we have a sampling. So we have the xi and the value of f for the different xi. We have typically n samples. And from these n samples, so you basically have n variables, you want to build up an approximation that I'll call fn of this function f. Now, in order to hope to be able to approximate well a function from a limited number of elements, you need some kind of regularity on the function f in order to be able to interpolate in the gap where you have no information. And the key question is what kind of regularity you can use and how to use it. Okay, when you have a classification problem, apparently the function is not regular because there is a jam when you say, if you have two classes, let's say between 1 and -1, but you can always retransfer that, which is almost always done, as an approximation of a regular function. You define f as the sign of a function f tilde, so basically the level set, and this function here is the regular function that we're trying to approximate. That's what is always done in kernel learning, SVM, and so on. So we're always back to a problem of approximating a regular function. Now, regular in what sense? And how to compute fn. Again, these are always the same questions that are going to come. Okay, so what is doing a one hidden layer network? The idea is the following. You begin from x, which is a d-dimensional vector. And then you just apply a simple linear operator and you get a first output vector which is here. So each element here is just a linear combination of the input value here with weights which depend upon the output end. So you can also view it as an inner product between x and a weight vector that gives you, that's the value of the inner product. Now, the strange thing that these networks are doing is that then to this inner product, to which you may add up a constant, you put a non-linearity rho, which is here. So you put a scalar non-linearity all over, and then you make a linear combination of all the outputs, and you get an expansion, which is a linear combination of each value, and you get a function of x. Okay? And n is the number of variable, basically the size, in this case, of the hidden layer there. Okay. This is called a ridge approximation, and on this there is really no mystery. Almost everything is well understood mathematically. So I just would like to summarize that. What is this function? How does it look like? Rho of the inner product of Wn with x plus bm. This is a 1D variable. So this is called a ridge function. Why? Because it varies along a one-dimensional variable, but along all the other direction it will remain constant. Okay? So you are decomposing your function as a linear combination of these ridge functions, m of them. Now, the weights are going to be learned. They are going to be learned in order to get the smallest error on f from fn. Okay? And this is a nonlinear approximation. But you can relatively easily show that if you add up enough coefficient here, the error is going to go to 0. Now, this theorem is often quoted as the reason why neural net can be powerful, blah, blah, blah. No, this is a simple result, and there is no gain with it. In what sense there is no gain? Getting an approximation of a function with another one index, and when m goes to infinity, getting an error that goes to 0, you have that in any basis. The problem is not to have an error which goes to 0. The problem is to have an error which goes extremely fast to 0, so that with few elements you can approximate your function. That's the problem. Okay? A theorem which tells you the error goes to 0 is, in this kind of problem, useless. You need speed of decay. Now, so that's the first important thing. You still have the curse of dimensionality. And to show you why this theorem is not so spectacular, just put for rho of u the exponential e to the iu. Okay? It's one particular nonlinear function. What do you get? A Fourier series. You are just saying any function can be approximated in the Fourier domain when the number of frequencies is increasing to infinity. Yes, we all know that. The difficulty is, will your function be well approximated in high dimension with that kind of thing? The answer will be no. And still, the interesting aspect of this theorem is that it's not just true for Fourier, it's essentially true for any function rho. Okay, let me go to the type of function rho that is usually used. Rectified, which is a function which is 0 and then linear. If you make a linear combination of such functions like that, what are you going to get? Piecewise linear approximation. So let me go back in one dimension. In one dimension, if you have a regular function, and you do a piecewise linear approximation with an interval epsilon, at what speed the error will go to 0? If your function is a little bit regular, so a function which is called Lipschitz regular, that means basically the derivative is bounded, exists almost everywhere. So the difference between f of x and f of x prime is bounded by x minus x prime. If you have this, then you easily verify, obviously, that if x minus x prime is smaller than epsilon, then the error between f and its linear approximation will be smaller than c epsilon. In other words, if you cover your whole one-dimensional space with points at a distance epsilon. You need epsilon to the minus 1 point to do so. You get that, so you're going to get an error that decays like 1 over f. Good. Again, the problem is what happens when you go in high dimension. When you go in high dimension, the same result will apply. It's just that then you will have to do directional linear approximation with ridge functions. If you impose that your function is still Lipschitz, so x minus x, the difference between f of x prime is smaller than the distance between x minus x prime, you get the same bound, but how many points do you need m to cover your space? Epsilon to the minus d, and here you get your curse of dimensionality. The area is going to decay like 1 over d. So extremely small. You need a huge number of points. Good, so let's try to put more regularity of the function. Okay, Lipschitz is not a very regular function. What kind of regularity would a mathematician immediately imagine? Well, you put more derivatives. Instead of just having one derivative, why not putting more derivative? Let's say s derivative. What is that going to buy you? If you have s derivative, then instead of doing piecewise linear interpolation, you can do piecewise polynomial interpolation. And a polynomial interpolation will be much more precise, because the error between f and its Taylor polynomial will decay like x minus u to the power s, okay, instead of power 1. So if this is small, it's going to be very small. What's the good point of that? Well, that means if you want to have an error which is epsilon, now you have to sample your space at a distance epsilon to 1 over s. Epsilon is small, so you can sample at larger distances to get an error which is smaller than c epsilon. Why is that good? It's good because now the number of points that you need is not m to the power minus d, but minus d over s. And you will get that kind of balance. Okay. That doesn't solve your problem. Why that doesn't solve your problem? Because what is s? 1, 2, 3, 4. You are not going to put a polynomial of a degree 5,000 on here. And s to the power 345 divided by 1,000,000, you're still in Curse of Dimensionality. And that's basically the state of the art of approximation theory. You refine things. Instead of saying your function is s time continuously differentiable, you can make it in the Sobolev space, in the Bezoff space, but deep down you have the same kind of regularity measure. And it just doesn't work. And that's basically the failure of approximation theory for this kind of problem. We don't know in mathematics how to deal with very high-dimensional functions. Okay, so what does kernel learning do for them? Kernel learning begins from the point in RD with this horrible Euclidean metric. And then the idea is to do, you can do it as a kernel or as a change of variable. You do a change of variable. So you define phi of x, which is some kind of nonlinear transform. Some people speak of that as feature vectors. I'll call that a change of variable. And the idea is that you do that so that you can approximate your function by something which is now, by miracle, linear in your arrival space. A simple linear combination. So that's a 1D projection. So what that means, if you think of a classification problem, you take a nonlinear change of variable, and here in this new space of dimension d prime, this is again your, if you wish, feature vector, you hope that things are separated. And if things are separated, then it's wonderful because if you have a classification problem, you can just put a hyperplane that separates the two classes. What that means is that if you project orthogonally to the hyperplane, you'll have a linear combination which is going to discriminate your two classes. The key element is that essentially this new metric which appears here is probably much better to measure the similarity between the points. So the question is, obviously, that's a very good idea, but how can you find such a phi? And what kind of regularity on f do you need so that such a phi can indeed be found from a limited number of measurements? So there is obviously a naive way to do the problem is the following. Oh, what I need is to have a hyperplane to separate my samples. But if I push my sample in sufficiently high dimensions, let's say if you have n points, data points, and you put them in dimension d prime, which is larger than n plus 1, you can show that with probability 1, you'll have a hyperplane that will separate exactly the two classes that you need to separate. And so, the idea is to increase dimensionality. But there is a big problem. Yes, you're going to obviously separate your data in two parts, but you are going to do a gross overfitting. It doesn't generalize. And to see that, just take a very simple example, which is the Gaussian kernel. The Gaussian kernel defines an inner product, which is x minus x prime squared exponential, so it's a Gaussian of variance sigma. What's happening? What's happening is that essentially if you do that, for any points, you only look at the similarity with very close point at the distance sigma. So basically when you do that kind of thing, you do a nearest neighbor classifier. And a nearest neighbor classifier is not going to work out because, as I said, first of all, points are going to be very far, so the nearest point is going to be very far. And no reason why the nearest point is going to be good to do your problem. So, kernel learning is a very beautiful idea, but until now, there is no theory to understand how to build up this fireflies. Okay, there is another way to look at the problem to make sure that you're not going to do any overfitting, is to rather try to reduce dimension. So, reduce the number of variables. Okay, so let's say it. We are going to do a change of variable phi of x, but now we are going to impose that this change of variable has less variables. So what do we need in order to be able to make sure that we can solve the problem? We need to make sure that if f of x and f of x prime are different, so two different classes, phi of x have to be different than phi of x prime in order to be able to discriminate these two classes. But that will guarantee that you can write f as some function f tilde of phi of x. So that's indeed a change of variable. But what you need is really that f tilde is regular. If you want, let's say that f tilde is Lipschitz. So f tilde of z minus f tilde of z prime smaller than z of minus z prime. What kind, so that's a little bit more constrained. It's not just f tilde exists, but it's regular. You just replace z by its value, phi of x. So f tilde of phi of x is f of x. That means f of x minus f of x prime is smaller than phi of x minus phi of x prime. If I just revert this equality, what it tells me that my change of variable has to be discriminative. It has to reduce dimensionality, but the distance between x and x prime has always to be bigger than the distance defined by f. So it's going to strongly depend upon f, and that's necessary in order to preserve basically the different classes. Okay, so at what condition can I solve my problem with that kind of strategy? You can solve your problem if you reduce the dimension enough. Because now you have an approximation of a Lipschitz function over a d-prime dimensional variable. So if the map of your original domain omega, which is now phi of omega, is not too big, dimension d prime, you can cover it with m to the power with n points, you will cover it at the distance n to the power minus 1 over d prime, and you get the same kind of bound than previously, but the d is now d prime, and if d prime is small, it's okay, you will have enough samples. In other words, if you go from one dimension 1 million to a problem of dimension 10 or 1 or 15, you are perfectly secure. The big difficulty, obviously, is to find this miracle change of variable that is going to go from a dimension 1 million to a dimension d prime 15, let's say, without killing the information you need to discriminate it. And that's what we'll speak about. That's where the deep convolution networks comes in. So, one person whose name is particularly attached to that is Yann Lequin, because he's really the one who proposed this convolutional structure with these multi-layer networks. So, the idea of a deep network is that we're going to do the same thing. It's also called multi-layer neural networks, so there is nothing really new behind that. We are going to repeat what we did for one layer several times. So let me repeat. For one layer, you apply a linear operator, which will happen to be a convolution. And then you do a pointwise nonlinearity, and then you repeat. You apply a linear convolution, your pointwise nonlinearity, until you get your change of variable. And from your change of variable, you just do a linear combination, and you get the output. Now, in this huge network, you have these linear operators. They are big matrices with typically more than a billion variables. And you are going to optimize the weights of these matrices so that the error is as small as possible on the training data. So that for the xi that you put in, you know the value of the yi, and you try to make sure that your network is outputting the right value. And you do that with stochastic gradient descent. So, another important thing is that there are architecture constraints in these networks. And these architecture constraints are very important because they are the ones that define the class of function that you'll be able to approximate. And convolution is one of the elements. The big surprise was the fact that you get absolutely exceptional results with that kind of thing. So you have to realize that if I take, for example, computer vision, things essentially couldn't scale until the years, let's say, 2010. There were beautiful algorithms, things that were working on a relatively limited framework, but unimaginable to address problems like the ImageNet classification problem that I'll be speaking about. I couldn't imagine that there would be cars driving automatically in the street within the next 5 or 6 years. These are really brutal change on the state of the art. Speech processing has been improved a lot. Language, biodata, and so on. What is very interesting in these networks is not so much that it applies to images. It's the fact that they seem to capture something sufficiently generic to solve general high-dimensional approximation problem, including physics, as I will show. And obviously the question now is, why does it work? When does it work? What kind of property does it suppose on the function that you are approximating? Now, one of the elements that appears is that as you go deeper and deeper, you build more and more invariant representation. And there is a scale phenomena. The invariants are built up hierarchically. There is another very important phenomena, which is a linearization of very nonlinear phenomena. And that will be another important mathematical aspect behind all that. Now, what I want to emphasize is that it's a difficult problem. It's a difficult problem, and I'll show that by relating it to physics problem. If you take the problem of turbulence, doing statistical physics of turbulence is essentially a totally open problem in physics, which has not much moved since the early work of Kolmogorov in the 40s and 60s. So for the last 60 years, the brightest minds have been working on that kind of very high-dimensional problem. And I'll show you that these deep networks are able to simulate things which are close to turbulent fluid. So that shows that they are really attacking very sophisticated properties. Okay, let me go to ImageNet. So ImageNet is this database with 1 million images and 2,000 classes. And you have this very spectacular result by Krzyzewski, Stéphane, and Hinton, producing earlier on a 5-layer neural network. First layer had oriented filters that are relating it to wavelets. The error was 15%. Now you have networks with 150 layers, which goes with an error down to 5%, which is of the order of the errors of humans on this database. So to show you the level of difficulties of these images, this is a meat countenance ship, motor scooper, leopard, and so on, a car. These are the answers produced by the network, and in pink you have the appropriate answer. So it's interesting here, for example, this could be seen as a convertible, as well as a grid, as well as a pickup, beach wagon, and so on. It happened that the right answer was grid, but it could have been a beach wagon, which shows the ambiguities also in that kind of thing. The fact is, it's really spectacular. Yes?
The performance of the digital networks has been derived initially in mathematical form, or this is how we explain the results?
These are experimental results.
No, I mean, like, you made the point with the math that it's really hard to fit difficult problems.
Yeah.
Also because of the high dimensionality. The results which have been achieved with the digital networks have been proven to work on math on paper in
No math.
before, or they run it
They just, this is an empirical field right now, okay? Nothing is proved on math. Nothing on the performance of these. These are the open problems. And, but that's normal, okay? When you have a difficult problem, mathematics always comes after. It's almost never the case, the counterexample being always the same, Einstein, and so on. It's almost never the case. You always have experimental people who are discovering the phenomena, and then theoretical aspects comes after. And that's what's happening. Now, what's happening is that the field is essentially experimental. Because the mathematics are difficult, so anybody interested in doing math is more than welcome, because there are beautiful things to do. But yes, we don't know how to prove this. These are just experimental results obtained by algorithms. This is typically a scene labeling for a car driving, so you see the road, the buildings, the people, and so on. All this is done automatically on the fly, and is sufficiently reliable so that you have now automatic cars driving in the streets. Okay, so in a very nice paper by the following authors, still, they showed something is you have to be careful about error and trial strategy, because these are images. This is a very small error that was added with the purpose of tricking the network. These are images which are identical visually to these ones, and they are now all classified as ostriches. And that's a problem if you are flying in an airplane which is controlled by a deep network. Personally, I wouldn't go into the airplane. As long as you have no math, you have no guarantee of sudden instabilities and so on. And even though you may not like doing math, that's at least one reason why you should invest or have people invest in understanding a little bit what's happening. You need to guarantee some reliability. Yes?
Is there a secret explanation of how it happened?
Yeah, in this case, yes, because it happens that the network, I'll show that, had matrices which were slightly amplifying. I'll explain that on the way. This problem here is understood, and in fact was basically understood by the authors where they put it. Okay, let me go to the network. Basically, the way this network works is you begin, I'll show always most of the examples from images because it's easier. You have an image, you have an operator which produces multiple images and your non-linearity. Now, how do you go from a layer j-1 to a layer j with these operators? But as I said, these operators are structured, and they are structured with convolutions. Basically, each image here is computed with a filter that is applied to each of these images. Okay, so you make a convolution, and then you sum all these convolutions, and you get your results. Okay, so you have a sum across channels. Now, what about the non-linearity? The non-linearity, the important property will be that it's a contractive non-linearity. Rho of u minus rho of u prime is always smaller than u minus u prime. So it may be a rectifier, an arctangent, it may be a modulus, but contractivity will be important. That will be important for reducing dimensionality, contracting the space. Now, about the question that you asked. These operators here had a norm larger than 1. So when you cascade operators of norm larger than 1, despite the nonlinearity, you can have a phenomena of amplification, and a small error puts a very big error at the output. Okay. There has been also work on synthesis, and this work, among the work by this very nice baby here, shows some very interesting linearization elements. So basically, in some sense, they inverted a deep network. So from a low-dimensional outputs, and they do that in a slightly different framework with competitive networks, you have now this output that you put at an input, and you generate an image. Now observe that kind of thing. This network was first trained for faces. So you have the small vector corresponding to one face, another small vector that synthesizes another face, a third, a woman. Now you take these 3 vectors, you take the first one, subtract the other one, you add up the third one, you get a vector, you reconstruct, you get a woman with glasses. What does that mean? Putting glass, this is an incredibly nonlinear effect on the image. Gender, this is a completely nonlinear effect. And what looks like is that in this space, this is the phi of x, things almost have been linearized, and you can add up, subtract these different qualities as if they were belonging to different directions. If you do the same thing directly on the image, you obviously don't get at all that, you get an image which is ugly. Same kind of network built on bedrooms. This is a bedroom image produced by a small vector. This is another bedroom image produced by another vector. Then you take your 2 vector of dimension 100 and you do an interpolation, and for each intermediate vectors you reconstruct. That's the middle one. The amazing thing is that it looks like a bedroom, and a different bedroom from this one and this one. As if the bedrooms had been linearized. Imagine bedrooms as being some weird manifold, completely flattened out at the output. So you have a phenomena of linearization which is coming in, these problems. And that's one of the remarkable properties. So there are many questions here. Some relatively easy. Why convolution? Convolutions because many problems are translation covariant. What happens here or here has the same kind of meaning. So if you want to reflect that, you use an operator which is covariant, and namely it has to be convolution if it's linear. Why no other fitting? Why in this case? Because you are doing contraction with this, and if you make sure that these operators are bounded with a norm smaller than 1, in fact reduced dimension, you create variables, but in a progressively smaller dimensional space. So you don't overfit because you contract the space. What is much more complicated? Okay, why cascading all that? Why would you do something better than a 1-layer network? Why introducing nonlinearities? How and what to linearize? How come these things linearize? What are the roles of all these channels? And so on. Yes? Yeah. Yeah, up to, if you scale you can put it below the line. So up to a multiplicative constant it is. And the multiplicative constant you can get rid of it. So it's essentially contracted. So I'm going to try to address some of these questions across the different lectures, and in particular the next 2 hours. So, dimension reduction. That's the strategy we'll follow. Yes?
Convolution and inner product is the same thing, right?
Yeah, well, an inner product can be much more general. Here the convolution imposed that the inner product here is going to be translated, basically. It's the same filter that you apply all over, okay? Okay, dimension reduction. There is one way to reduce dimensionality that everybody knows is principal component analysis. Basically, it's a linear operator. Now, under what condition can you apply that? We're going to look at the level set. The level set are the set of x for which f of x equals t. In other words, level sets are the different classes of your function. Okay? If you want to reduce dimension with a linear operator, in other words, you want to erase a variable that is useless, what do you need? You need that your level set have to be parallel to a linear space. If you have that, boom, you do a projection, you have a new variable in a lower dimensional space, and everything is great. The problem is that that's never going to be the case. That's the level set in a real problem. It's a mess. It's irregular, it goes all over, and so on. So if you brutally apply a linear operator that reduces dimension, you are going to kill your problem. Okay, you are going to lose all precision. So what you could dream of doing is to linearize your level set, to make them nearly linear. I put them here brutally linear. Because if you find a change of variable which nearly linearizes the problem, then boom, you can project. Now, this strategy of linearizing a problem with a change of variable is not a new strategy. You do that all over in mathematics. You have a set of nonlinear PDE. You try to find the change of variable which linearizes your solution. Okay. The only difference is that here we are in very high dimension, so the problem is going to be much more difficult. And it's difficult because also you don't know this level set. You just have few points in your level set. This is the situation in which you are. I'm just going to choose two level sets. I have two level sets, and you have few points that you know completely spread, isolated in the space. What does that tell you? When you have a problem where you need to linearize a surface, the first idea that comes to mind is to try to compute the curvature and to flatten up your surface. But you can't compute the curvature because you just have a point and you have no close point. So you cannot work locally. That's the important thing when you are in high dimension. So you will need to work globally. And you need to characterize the geometry of these sets globally. How do you do that? Look at the symmetry of your sets. That's the mathematical tools that you have in hand when you want to characterize global properties. So what does that mean? You are going to look at operators that I call G here, such that the operator G is a symmetry. What does it mean that it's a symmetry? That it takes any point of a level set and it moves it to another point that belongs to the same level set. So a blue point goes to a blue point. In other words, the value of the function at gx is the same as the value of the function at x. What that means is that f is invariant to the action of g, so it's a global property. These symmetries, if you take all of them, completely characterize the geometric property of your level set. Now, one of the important properties about symmetries is, of course, if f of gx equals f of x, if you make a composition of two symmetries, it's still a symmetry, because f of g1, g2x will be the same than g1 is a symmetry, f of g2x, same as f of x. So, composition of symmetry remains symmetries. Symmetries define groups. And that's where we move yet to another chapter of mathematics, which is group theory. So we'd like to understand groups to try to describe these properties. So what is a group? A group is a set of elements. These will be operators acting on our data, such as the composition of two elements still belongs to the element. Each element has an inverse. A group element is like a displacement. Think of it as a movement in the space. So you can revert the movement, the associativity. And if you are the luck that it commutes, it's called a commutative group. In general, that's not going to be true, but we'll begin with this property. Now, a group, like a space, you can define its dimension. What is the dimension of the group? Is the number of generators that allows you to move, to get all the elements of the group. So if you are in dimension n, that means that you have n generator, and if you iterate over the n generator, you can get any element of the group. So then you'll say you have a finite dimensional group. Now you have yet another notion, which are Lie groups. What is a Lie group? Is when the movement defined by the generator can be infinitely small. I'm going to illustrate all this on examples. But this is an important concept to try to understand the properties which are behind all that. Okay, let me make it practical. Let's take the case of digit recognition. You take a 3. If you translate the 3, it's still a 3. So it has the same class. So it's a problem which is translation invariant. Here the group is the translation group. You take a point, you move it, it's a group, it can be reverted, composition is still a translations, and so on. Now, this is a small group because it only has 2 parameters, 2-dimensional group. It's not very useful to have a small group because if you want to simplify the problem, to build an environment, you want to reduce the dimensionality. Here you're just going to reduce the dimensionality by 2 parameters. Not very interesting. You have groups which are much bigger. Take the 3. If you deform it a little bit, you still have a 3. If you deform it too much, you can have a 5. If you deform it a little bit, you get a 5. If you take images, if you deform them, you can travel across the whole Italian painting. This is called diffeomorphism group. It's the groups of all deformation. This is a huge group. It's a huge group, huge number of parameters. And what is interesting is you see when the deformation is small, it's still essentially very similar, same class. When the deformation is too big, obviously you'll get out. So that will be the kind of group we'll be much more interested in to be able to reduce dimensionality. Let me show you other groups. Here. Heard that. The next, this is a time frequency picture I'll show you, but the important thing is this is frequency. Same thing.
Encyclopedias.
Okay. Same word. 2 different pictures. These different pictures are changed. In frequency, they are basically deformed in time and frequency. The group that is going to come in are translation, deformation, not just in time, but time, frequency. If you look at that, you see how you go from one word to the other. Deformation in this new space. If you take images, you can have rotations. So then the groups will include the rotations and potential deformation. You can have scaling. So you can have many groups. We'll see that deep networks can deal with much, much more complex groups because we saw addition of classes, things like that. This is much more complicated than these simple geometrical groups. What's going to be the difficulty? And I'm finishing in 5 minutes. Yeah. The difficulty will be the following. You are in your space X, and this is a level set. And the fact that it's a level set, if you take the symmetric group, in other words, if you move along the level set with the action of one group element, G1, and you repeat G1 and so on, G1 p times, you're going to get a trajectory which is horribly regular. If you take another point x prime, it will also be a mess. What you would like to make the problem simple, linear, and so on, you would like to find a change of variable so that these trajectories get very nicely regular, almost linear. That means when you move, you basically move as if you were on a very regular curve or nearly straight. That will be the problem. Can you find a change of variable that transforms your problem in something as simple? And the condition for doing that is that you see the distance you move in your Euclidean space, which is phi of x minus phi of x moved by g, has to be of the order of the size of the group elements, which is given here by the norm of g. That will be a Lipschitz condition, and that will be one of the very important regularity conditions. Can we create a network which does that?
Sorry?
Yes?
You J not translation but a diffeomorphism? How do you define norm of J?
Very good question. That will be the next one. How can you define the norm of J for diffeomorphism? So I'm going to look at small diffeomorphism because that's where I can hope to be invariant and then try to define distortion. Before addressing diffeomorphism, let me just begin with translation. So you would like potentially to be even invariant by translation. That means that if x is translated, the function doesn't depend upon this translation. And of course, in this case, it's also legit. That's even more powerful. With diffeomorphism, what is a diffeomorphism? It takes a function x of u, and instead of just translating the function x of u, it translates the function by an amount which depends upon u. So tau now is a regular function of u, so that it's going to squeeze, dilate, and so on. Now, by how much it's going to squeeze or dilate the distance, you can just take the Jacobian of tau, and you take the maximum size of the Jacobian. That gives you the amount by which the distance will be changed. And this is defined as the weak norm of a diffeomorphism. So in this framework, you would like to get something like that. This is totally wrong if phi is identity. You would like to find a phi which is continuous, Lipschitz continuous, to diffeomorphism. Okay? Now obviously that's not difficult to get. Get phi equals 0 and you get this property. So there is this last missing bit, you still have to be discriminative, which was the property we begin with. You need to make sure that the distance between phi of x and phi of x prime has to always be bigger up to a constant to f of x minus f of x prime. You need to get all these things, and phi of x has to be of relatively small dimension. So, the problem is how to build up such a thing. And what I will show next time is that to build up that, you are naturally led to a deep network architecture. To explain why this is difficult, I'm just going to begin with the obvious solution that comes to mind to anybody who spent a little bit of time studying math or did physics, Fourier transform. If you think of the Fourier transform, what's the obvious first thing that comes to mind? You take a function, you compute the Fourier transform. So the Fourier transform is the correlation of the function with sine wave. If your function is translated, the Fourier transform is just going to be modified by a phase. So if you want to have something which is translation invariant, not difficult. You just kill the phase. You take the modulus of the Fourier transform of x, or x translated is the same. So you have a representation which is translation invariant. What's happening now if you deform your function? So take a function that you deform. This is a Fourier transform with two bumps. A low frequency bump, a high frequency bump. If you do a small deformation, which is just a dilation, it's going to dilate the Fourier transform. So at low frequency, it's going to move it a little bit, but at high frequency, it's going to move it a lot. So now, if you compute the subtraction of these two functions, which is here, even though grad of tau in this case is epsilon is very small, this is going to be big. In other words, high frequencies are unstable to deformation. This is why nobody used the Fourier transform to do image classification, speech classification, whatever, classification problems. So we'll need to replace the Fourier transform with something else. And what I'm going to begin with next time will be a simplified convolution tree. Normally, a convolution network, each element here is computed by a linear combination of all the previous layer images. Here, I'm going to impose something simpler. Each image here is computed by convolution from one image here. So just a tree. And we are going to see how far we can go by simplifying this network and just imposing a tree. And I'll be showing you that you can do a lot of classification of simpler problems that you've seen but still complicated. You can even do quantum physics just with that. But we will see it's not enough. And that will be next time.
For a couple of quick questions. Yeah,
layer should be able to represent the exact same mathematical function. Is it just a matter of computational complexity, or?
Okay, that's important. You're right. Convolution network is a particular case of fully connected case. So why not putting much more variables? Because you need to learn them. And you have a limited number of data. That's your problem. The goal here is not to produce the most general architecture. The goal is to produce the simplest possible architecture which can still run. And getting incredibly general architecture is not difficult. You just take the architecture which works and you put more variable and it's even more general. It's the reverse which is hard. How can you get rid of parameters in the architecture? How can you simplify it and still make it work? But the point is, you're right. And what's happening now, in fact, what was interesting if you look at this deep net is that before, let's say, until 1 year ago, the last layers of the deep network were fully connected. Now they are not. They're all layers are just convolution, non-linearity, convolution, non-linearity, and a soft max at the end.
Let's thank Stéphane, and tomorrow